non-homogeneous linear differential equations with constant coefficients are the same kind of problems we were doing, just with right-hand side not zero. This amounts to the problem like the mass of the spring plus a forcing function, something in addition to the spring and the damping that pushes the mass. Or in the RLC circuit, you attach a voltage. That makes an impressed voltage that makes the right-hand side non-zero. So here's the second order equation. This is really what you need to know for most applications is the second order case. And higher order cases tend to, if you look ahead a little bit, be very similar to these, just a little more complicated, but it's the same concept. So suppose we have d squared y dt squared plus p of t times dy dt plus q of t y equals f of t. This is a second order linear differential equation. Just instead of 0 on the right hand side for homogeneous, we have a general function of t on the right hand side, which makes it non-homogeneous. Suppose we have one solution to this equation. We'll call it yp of t. Some function we plug in here that satisfies the differential equation on the given solution interval. And we let y of t denote an arbitrary solution. We want to find all solutions. We only know one. What could all solutions of this be? Well, let's define yh to be y, the arbitrary solutions, a set of solutions, minus yp, the one solution that we found. And we plug yh into the left-hand side of the differential equation, right? We take second derivative plus p of t times the first derivative plus q of t times yh itself. What do we get? Well, yh is y minus yp, so you put that in. And then the derivative of the difference is the difference of the derivative. Same thing with the second derivative. And multiplication distributes. And you can then separate these terms into the ones that involve y, and the ones that involve yp. And when you group them into two groups, you realize all of a sudden that because y represents an arbitrary solution, doesn't matter which one it is, you always get from this, in the differential equation on the left, f of t on the right. So this is equal to f of t. Similarly, yp is one solution, so when you put it into the left side, you also get f of t. This is f of t minus f of t. It's 0. What does that tell you? That tells you that yh is all functions that if you put them on the left side of the differential equation, they give you 0 on the right. In other words, yh is the general solution of the associated homogeneous problem. If you take an arbitrary solution, subtract off any one solution, the set of all functions that can satisfy that is the general solution of the homogeneous problem. Now you rewrite it in the other order and say, well, if yh was yp, it was y minus yp, then we can add yp over to each side, and we find out the set of all solutions to the non-homogeneous problem is equal to the general solution of the homogeneous problem plus any one particular solution. That seems astonishing at first. All you have to do to solve a non-homogeneous problem now is find the general solution of the associated homogeneous problem, where you put 0 on the right-hand side. That's the problem we just did. Plus add any one solution whatsoever to the non-homogeneous problem, and now you've got them all. So this is a nice result. I want to compare it to something down below here. Let's see. Geometric analogy. Suppose you have in linear algebra a plane, right? It has this general equation: ax plus by plus cz equals d in 3 space. A plane in 3 space. This is a general plane. How can you get to any point on the plane? One way you did it, maybe I should draw a picture here. Goes this way. If you want to get arbitrary points in the plane, what can you do? You can take a vector out to any point whatsoever on the plane P, And then within the plane, take a multiple of one vector, say this one, v1 or something, and this one, v2, and you can get to any point in a plane by taking two vectors in the plane that don't lie along the same line. We call those linearly independent. And we go at any a particular, if we want to get to this point here, let's say, we can get to this point here in the plane from here, from P, by moving a multiple of this vector plus a multiple of this vector, right? We take this one and go that many times its length, maybe twice its length. So maybe it's twice this one's length plus twice this one's length or something. And we can get to any point in the plane by first moving out to P, and then once we're in the plane, we take a multiple of this vector out here, plus a multiple of this vector out here, and we get to the point that we want, Q. This is exactly the analogy we have to what we're doing with differential equations. In differential equations, we take any particular solution of the differential equation, we get out to a plane of solutions that's spanned by a multiple of one solution plus a multiple of another. That's what we found for homogeneous problems. The general solution was an arbitrary linear combination of any two solutions. C1 times 1 plus C2 times the other. And then we add that to any particular solution of the non-homogeneous problem, and we get the set of all solutions to the differential equation. So it's this same nice analogy that we have from doing planes in space in linear algebra. All right, that greatly reduces our work because all we have to do is find one solution to the non-homogeneous problem and apply our previous techniques to solve, find all solutions of the non-homogeneous problem. For instance, suppose I want to find all solutions of y double prime plus 9y equals 9. Well, what can I do? Well, maybe I can kind of guess one. It's kind of obvious. If I want to get a number on the right, maybe I could plug in a number for y on the left, and the second derivative would be 0 if I just put in y equal a number. What do I need to put in here? I need to put y equals 1, so 9 times 1 equals 9. So one solution I can kind of guess is y equals the constant 1. That satisfies this differential equation. All I have to do now is add that to the solution y double prime plus 9y equals 0. Well, what's that? I know how to solve that already, right? Y double prime plus 9y equals 0. I'll call this yh double prime. We're solving the general solution of a homogeneous problem. We'll call that yh. And this has characteristic equation 9 squared plus r squared plus 9 equals 0, recall. And the solutions of the characteristic equation are plus or minus 3i. Right? You can subtract 9 and square root both sides to find that. Or you use the quadratic formula. And so we know from our previous theory that it has general solution c1 times e to the 0 cosine 3t plus c2 e to the 0t sine 3t. It's just c1 cosine plus c2 sine of 3t. And then we know that one particular solution of this problem is yp of t equal 1. We'll call it a little p here, referred to the particular solution. And so the general solution in the form of all solutions to this problem is just all solutions to this problem, c1 cosine 3t plus c2 sine 3t, plus one solution to this problem, the original one, 1, and that is done. Right? We've got all the solutions. So it's a 1, 2, 3 method. Find any particular solution whatsoever. Find the general solution of the homogeneous equation, and then add the two together. Well, it's actually usually better to find the homogeneous solution first. So we're going to do that in these problems because that sometimes gives you a hint on how to find the particular solution, as we're going to find out. In these equations with constant coefficients, a y double prime plus b y prime plus c y equals the function of t. There's a particular method that's really nice for solving these. If equations that are non-homogeneous, and these come up a lot in practice, but the best way to find it is first find the homogeneous solution. And here's the table that tells you how to guess. I kind of guessed a particular solution in the last problem. Here's the method of judicious guessing, you might call it. My differential equations professor called it that. If you see f of t on the right-hand side of the differential equation looking like this, for an equation with constant coefficients only, then this method tells you it's a theorem. This table is a theorem. That there is a function of this form that you can plug in, and it's a solution. Right? Before we found that when the right-hand side was a constant, I just plugged a constant in, a different constant, but nonetheless a constant function was the form of the solution. And I could figure out by plugging in what that was. Similarly here, if I just had a constant, this is what this first line tells me, if I just have a constant alpha 0, a 0th degree polynomial, then I can guess the solution is a constant many times the power of t. And if I have a first order polynomial on the right hand side, a constant times t plus a constant, this table tells me I guess a constant times t plus a constant times possibly some power of t. What power of t goes in there, and so on and so forth. In general, if a polynomial of nth degree is on the right side of your differential equation with constant coefficients, linear with constant coefficients, then you guess a solution that's also an nth degree polynomial, possibly all times the power of t. What power do you need there? K is the smallest whole number. Whole numbers are 0, 1, 2, 3, 4, and so on forever. The smallest whole number that makes every term in this not a solution to the homogeneous problem that you get just by replacing the right-hand side with 0. Similarly, if you have an exponential function, e to the number times t, times a polynomial on the right-hand side of your differential equation, that tells you you can plug in a polynomial of the same degree, just with different coefficients, times the same exponential function, e to the same constant times t. All possibly times the power of t. And what power is it? It's the smallest power that makes each term in here when you multiply it out, not a solution to the homogeneous problem. And it's a cookbook. This tells you exactly what to plug in, just like we did in the last example. We saw a constant on the right-hand side, so we plugged in a constant. This tells you exactly what to plug in to find a particular solution. You just have to determine the coefficients. You plug in this form, and you see what the coefficients need to be to satisfy the differential equation. Hence, the method is called the method of undetermined coefficients. Furthermore, suppose you have a sine or a cosine times a polynomial of nth degree. Then you plug in a polynomial times a sine plus a polynomial times a cosine. You actually need both of these. If you have either sine or cosine or both, you need to use both over here. And the whole thing possibly times the power of t. Finally, the last one, boy, does this look complicated, is if you have a exponential times a sine times a polynomial, or an exponential times a cosine times a polynomial, you need a polynomial of the same degree times sine plus a polynomial times of the same degree times cosine times the exponential, possibly all times the power of t. It is true that once in a while, some of these coefficients are 0, so in that case, you really didn't need the whole thing, but in general, to solve the most general problem, you need a polynomial times sine plus a polynomial times cosine times an exponential, all times t to the k. If this seems too hard to remember, it actually all boils down to the last line of the table. The whole table actually is encompassed in this one single line. Talk about being compact. All you have to do is remember that. All these other lines up here are just special cases, right? If you put alpha equals 0 here, the exponential e to the 0t is nothing, and that goes away, so you get this line back, right? So when alpha equals 0, it's this one. If you put beta equals 0, then cosine is 1 and sine is 0, then you get this one. You just get the exponential times the polynomial. And if you put both alpha and beta equal to 0, then this is 1, and this is 1, and this is 0, and anyway, you get this line if you put alpha and beta both 0. You just have to think about it. So it's really all encompassed in this one line, this method of undetermined coefficients. And these are just put in here because these cases come up so often that it's nice to just think of them this way, so you don't have to be quite so complicated, but you know, well, this seems like a rather short list of functions. What about if it's something else on there in practice, like in electrical engineering and physical applications and lots of other ones too? This is exactly the kind of thing you tend to get on the right-hand side, and so this is exactly what you need to do to solve the problem. So this is actually real applied stuff. This is what comes up a lot in practice. And when you think about it, if you're putting a voltage in the right-hand side of a circuit, often you've got a sinusoidally alternating side, so you get either a sine or a cosine, or some combination thereof. If you have a battery put on the other side, that's a constant voltage, like the problem we just did. Lots of those things come up in practice, so this is exactly what you want to be able to do most. For the functions that are on the table, fortunately, there is another method coming up. It's just harder. But this method of lucky guessing, the form of the solution, and then just plugging it in and see what the coefficients are, that's a lot easier, right? So let's try that one for now. And here's this general strategy again. 1, solve the associated homogeneous problem by putting the right-hand side equal to 0. Find its general solution, C1 times 1 solution plus C2 times a linearly independent solution. 1, look up in the table the form of yp to determine the coefficients and get the particular solution. And then 3, add the two together. Here's a great example. Suppose I have this differential equation. D squared y dt squared plus 3dy dt plus 2y equals t. What do I have to do to solve this one? Step 1, I look at the homogeneous problem. I put 0 over here. There it is. How do I solve that one? I use the characteristic equation. R squared plus 3r plus 2 equals 0. And I factor this or apply the quadratic formula. I find that r can be -2 or -1. Those are the two solutions of it. So the general solution, well, two independent solutions are e to the minus 2t and e to the minus t. Remember that? And the general solution is an arbitrary linear combination of them. C1 times e to the minus 2t plus c2t and c to the minus t. So that's what we did before. There's the general solution of this equation with 0 on the right-hand side. We'll call that yh. Then what does the table predict? If you look on the right-hand side, this is a first-degree polynomial, right? At plus b. B happens to be 0 in here, but it's still a first-degree polynomial. If you like here, alpha 1t plus alpha 0 out of the table. If it's a first-degree polynomial on the right, then you look for a particular solution. This is a first-degree polynomial times t to the lowest power, whole power, that makes the each term in that not a solution of the homogeneous problem. So first we try k equals 0. We just try a polynomial first degree as the solution because the right-hand side was a polynomial first degree. I'll try k equals 0. I'll just look for a solution. Gamma 1t plus gamma 0, where gamma 1 and gamma 0 are unknown coefficients, just constants. And I plug it into the differential, I look first at the homogeneous solution. The homogeneous solution doesn't have any constants or constant times t in it. It has exponential functions. If you put those in the Wronskian, you'll see they're linearly independent, but people from experience just know these constants and constant times t are independent functions from these. So we can put k equals 0, and each term will not be a solution of the homogeneous problem. So we look for a solution yp of t of the form gamma 1t plus gamma 0. Just plug that into the differential equation, and we get, well, the second derivative of this is 0, right? Two derivatives of first degree polynomial 0. The first derivative of this is just gamma 1, so we get y double prime plus 3y prime plus 2 times y is gamma 1t plus gamma 0. All has to equal the right-hand side of the original non-homogeneous problem, t. So there's what we get by plugging in yp is gamma 1t plus gamma 0 into the differential equation. This is the second derivative plus 3 times the first derivative plus 2 times yp equals t. What do the coefficients have to be? Here's how you figure it out. You group like terms. You've got one term in t, let's see, on the left, and this one on the right, and so you subtract t over, and you've got 2 gamma 1t minus 1t. Those are all the terms with t. Then you group all the constant terms. 3 gamma 1 plus 2 gamma 0 over here. All that has to equal 0. Now, remember from algebra, if you have a polynomial of degree greater than or equal to 1 equals 0, how many solutions can it have? Goes back to the fundamental theorem of algebra, actually, right? If you, a result of the fundamental theorem of algebra is that a polynomial of degree n has at most n solutions, right, including multiplicities. And so we can't, on an interval, make this equal to 0. We can only make it equal to 0 most one time since it's a first degree polynomial. There's just one solution to this, unless these coefficients are really 0, and then it's not a first degree polynomial, it's just a 0. So the only way this can be equal to 0 on an interval of t values is if both these coefficients are equal to 0. That's the only way you can do it. So we need 2 gamma 1 minus 1 equals 0, I'll write it this way. And we need 3 gamma 1 plus 2 gamma 0 equals 0, we'll write it that way, as a system of 2 linear equations and 2 unknowns. This is easy to solve, right? Actually, what you do for these in general is add a multiple of one to the other to get rid of a coefficient, and then you can solve for the one that's left. But in this case, we've already got it. We just divide this one by a half, and we get gamma 1 equals a half, and then we can plug it into the other equation. Here, 3 halves plus 2 gamma 0 equals 0, and we find gamma 0 is minus 3/4. Evidently, a particular solution will occur when gamma is 1/2 t minus 3/4. Put these into gamma 1t plus gamma 0. Now we know the general solution. That was step 2, right? Step 1, we found the general solution of the associated homogeneous problem. This was it. Then step 2, we found this was one solution of the non-homogeneous problem. This is it. We add those two together, and we get all solutions of the non-homogeneous problem. Easy as that. How about this one? Suppose the right-hand side was not t, but it's e to the t. How do I solve this equation? Well, I already have the homogeneous problem from the last example, right? It's c1 e to the minus 2t plus c2 e to the minus t, because it's the same left-hand side. So I solve this with the right-hand side equals 0 the same way, get the general solution to that. Call it YH, and now if f of t equals t, I go up to the second line, e to the t, I go up to the second line of the table, and I say for e to the 1t, alpha equals 1, times a constant 1, that's what I have, 1 e to the 1t. I look for e to the 1t times a constant, possibly times a power of t. And I take the lowest whole power I can to make the terms, there's only one term actually, not solutions of the homogeneous problem. Let's see. There it is. Well, e to the minus t, a multiple of e to the minus t is a solution, and a multiple of e to the minus 2t is a solution, but you remember from doing the Wronskian previously for the homogeneous problems, e to R1t and e to the R2t are actually independent solutions when R1 and R2 aren't equal. So e to the t times a constant is actually not a solution of the homogeneous problem. You can't write it as a linear combination of these. So we can look for a solution of the form gamma 0 e to the t times t to the 0. So we're just gamma 0 e to the t. So we look for a solution of that form, in which case its derivative is itself, right? Derivative of e to the t is e to the t, and so is the second derivative. We'll plug all of those into the differential equation. Here's y double prime plus 3y prime plus 2y equals the right-hand side e to the t. Plug it into the original differential equation to try and find a solution, a single solution of the form gamma 0 e to the t. Now, just like last time, we group like terms, right? We group all e to the t terms, we subtract this one over and group it all together. Well, actually, I guess I didn't write it that way here, but that's what I'm thinking here. You divide through by e to the t and have this. And this says 6 gamma 0 e to the t equals 1, so gamma 0 equals 1/6. But it amounts to the same. You're grouping all the e to the t terms equals 0. You can divide through by e to the t. You find that all this with the minus 1 over here is equal to 0, and gamma has to be 1/6. All right. So a particular solution was gamma 0 e to the t. We found out by plugging in that gamma 0 must be a 6, so the particular solution is 1/6 e to the t. What if it doesn't work? Not possible. This is a theorem. It always works. There is always a solution of the form listed in the table. You just have to plug it in and see what the coefficients are. What always comes out is you get a system of linear equations like this, like we just did, that you can solve. Remember, if you took linear algebra, you find that a system of n linear equations and n unknowns can always be solved to show that it has a solution, a single unique solution, an infinite number of solutions, or no solution, but you can always do it. You show which case it is. And guess what? In these cases, it always comes out to be the case of a unique solution if you did this correctly. You'll always get the exactly one solution case. So it always works, gives you exactly the one solution. Here's the general solution then. Y is the general solution of the associated homogeneous problem plus the one particular solution we found. Well, how about this one? Y double prime plus 3y prime plus 2y equals e to the minus t. That looks just about like the last one. Maybe the solution is about the same. Once again, the general solution of the homogeneous problem is c1 e to the minus t2t. I can't talk that fast, guys. c1 e to the minus t equals c2 e to the minus 2t, because it's the same left-hand side equals 0, so it's the same homogeneous problem. The right-hand side from the table has to be, as before, gamma 0 except e to the minus t all times t to the k for some constant gamma 0. Now with k equals 0, this particular solution comes out to be gamma 0 e to the minus t, but wait a minute, that's the solution of the homogeneous problem, right? Here's the homogeneous problem. If I took c1 equals 1 and c2 equals 0, c1 equals gamma 0 and c2 equals 0, this is actually one of the solutions of the homogeneous problem. So I can't use it. I have to raise k equals 1. With k equals 1, I get gamma 0 e to the minus t times t to the 1 out of the table. And this one is not of the form of a homogeneous solution, right? You don't see a t e to the minus t. You can plug it in the Wronskian and see they're independent, but people know from practice that if there's a t e to the minus t, it's independent of e to the minus t. So this is the first power of t that makes the right side of the table not a solution of the homogeneous problem. So there must be, by the theorem, by the table, a solution of this form. Now we have a little more difficulty calculating the derivatives, right? If particular solution we know exists of the form gamma 0 t e to the minus t, its derivative is this, first derivative. Its second derivative is this. You have to use the product rule. And now you plug that in. Here's the second derivative, right? Let's plug the second derivative. So second derivative plus 3 times the first derivative plus 2 times yp equals the right-hand side e to the minus t. That's what I get when I plug into the differential equation, the original one. I'm looking for a particular solution. Now I group like terms. I group all the terms of t e to the minus t. This times this, and this times this, and this all together, and they look like that. I group all the terms together with e to the minus t times the constant, and I put 0 on the right-hand side. I have to subtract this one over to do that. That's where the minus 1 e to the minus t is. So I group the like terms, all equal to 0, and now, since t e to the minus t and e to the minus t are linearly independent, remember the definition of linearly independent? Two functions are by definition of linear independence. If you have a constant times one function plus a constant times the linearly independent function equals 0, the only constants that work are if both of these are equal to 0. It follows that both these have to be equal to 0. Well, one of them already is 0, right? Gamma 0 minus 3 gamma 0 is minus 2 gamma 0. Added to gamma 0 is actually equal to 0 already. So we're only left with one equation for the one unknown gamma 0. And this says, let's see, 1 gamma 0 minus 1 equals 0. Evidently, gamma 0 equals 1. So you put gamma 0 equals 1 into yp equals gamma 0 t e to the minus t, and you get 1 e to the minus t is a particular solution found by the method of undetermined coefficients. The general solution is now the general solution to the associated homogeneous problem, plus this particular solution to the non-homogeneous problem that we just found. There it is, all solutions to the non-homogeneous problem. Well, it gets tougher. How about this one? Y to O prime plus 3y prime plus 2y equals sine t. I've tried to make this one actually as simple as possible. It's not too bad. But you solve the associated homogeneous problem. That's c1 e to the minus t plus c2 e to the minus 2t. And now line 3 of the table tells you, where you have polynomials times sine and cosine, that you actually need both terms. If you go up here, if you have a 0th degree polynomial, beta 0 times sine, what do you need on the right? You need a 0th degree polynomial gamma 0 times sine plus a 0th degree polynomial delta 0, and here gamma 0 times cosine beta t. Well, beta is 1 here, so what we need is a constant times sine 1t plus a constant times cosine 1t, possibly times the power of t. The lowest power of t that will make each of those terms not a solution to the homogeneous problem. So, we tried k equals 0. Gamma 0 cosine t plus delta 0 sine t is what the table tells us we have to put. For some gamma 0 and delta 0, we hope that's going to work. How do we know? We just need to know that each of these terms is independent of these. And it is. Remember from the last section that cosines and sines are independent of exponential functions. So we're going to do that. We're going to take k equals 0 in the third line of the table and say there is a solution, gamma 0 cosine t plus delta 0 sine t. Because both these terms are independent, they aren't solutions of the homogeneous problem. So we plug the two terms in there. The first derivative is minus gamma 0 sine t plus delta 0 cosine t. The second derivative is minus gamma 0 cosine t minus delta 0 sine t. So we plug that in. Here's y to O prime plus 3 times y prime plus 2 times y, all equals the right-hand side sine t. And if we subtract the sine t over and group like terms, we have sine t times a bunch of stuff plus cosine t times a bunch of stuff equals 0. Remember, sine and cosine are independent. You wouldn't think so since they're the same shaped wave just moved over, but they actually are. The Wronskian proves it, right? Since these are independent functions, we know that the linear combination of them is 0. If and only if both coefficients are 0, that says this has to be 0 and this has to be 0. The first equation says minus 3 gamma 0 plus delta 0 equals 1. The second one says gamma 0 plus 3 delta 0 equals 0. As always, it's the same number of linear equations as unknowns. This will have, and it will have a unique solution. And so we just have to find it. How can we find this one? This is harder than before. We can't immediately get one solution. One way to do this is to add 3 times the second equation to the first one. Suppose I add 3 gamma 0 to minus 3 gamma 0, then they cancel, right? Then I've also got, right? And I've got to add 3 times this one to this one, 3 times this one to this one, then I'll get an equation that holds, right? I'll take 3 times this equation, add it to this equation, I'll get a true equation, right? So 3 times this added to this is 0, 3 times gamma delta 0 added to 1 delta 0 is 10 delta 0, equals 3 times 0 added to 1 is 1. I have 10 delta 0 equals 1 by adding 3 times this equation to this equation. That means that delta 0 must be a 10th. Now I can plug that back into either equation and solve for gamma 0, and I find that gamma 0 must be minus 3/10. I've shown that there's a particular solution of the form yp equals gamma 0 minus 3/10 cosine theta plus delta 0, 1/10 sine theta. The general solution of the problem is then the general solution of the associated homogeneous equation plus this particular solution of the non-homogeneous problem that I just found. Pretty complicated, huh? All right, let's do one more. The pièce de résistance, I can't even say it in French. All right, de résistance, something like that. Suppose I have y to O prime plus 3y equals 12t, y prime. This differential equation has a different left-hand side. Let's find its homogeneous general solution. So I put the right-hand side equals 0 and call this YH. I have the characteristic equation r squared plus 3r equals 0. So I factor that, r times r plus 3 equals 0, and I find r can be 0 or minus 3. So it has general solution c1 e to the 0t plus c2 e to the minus 3t, while e to the 0t is just 1. So one solution of the homogeneous problem is 1, and I get c1 times 1, and another solution is e to the minus 3t, so I get c2 e to the minus 3t added. Here's all solutions of the homogeneous problem. Now I look at the original problem, and I look in the table, and the table says, since the right-hand side is a first-degree polynomial, I'll look for a solution that's a first-degree polynomial, possibly times the power of t. So I think of this first. Here's the right-hand side. I look for a solution in this form from the table. If k equals 0, right, t to the 0, then I'm looking for a solution gamma 1t plus gamma 0. But wait, one of those terms, gamma 0 by itself, is a solution to the associated homogeneous problem, right? A constant, or a constant times 1 if you like, is a solution. So I can't take k equals 0, but the last term here, gamma 0, will be a solution of the homogeneous problem. So I need to try k equals 1. T times gamma 0 plus t squared times gamma 1. And now I notice there aren't any t's or t squareds in here, so that will be okay. I know from the table that there will be a solution of the form gamma 1t plus gamma 0 all times t to the 1. I plug this into the differential equation. The second derivative is 2 gamma 1. The first derivative is 2 gamma 1t plus gamma 0. And so I get, I just plug it in the left-hand side, 2 gamma 1 plus 3 times 2 gamma 1t plus gamma 0 equals the right-hand side 12t. I have to find out what the coefficients are. Well, I regroup them to have the t terms and the constant terms like we did in the earlier problem. All equals 0, I subtract the 12t over here too. There it is, minus 12t on the left. And now I notice that for this to vanish on an interval, once again, I need both coefficients equal to 0. That amounts to two linear equations. This one's this equation, this one equals 0 is this equation. Fortunately, I can solve this without any trouble. I divide by 6 and find that gamma 1 is 2. And then I plug that into the second equation and find gamma 0 is minus 4/3. So there's a particular solution, 2 times t squared minus 4/3 times t. General solution of the non-homogeneous problem is the associated, the general solution of the associated homogeneous problem plus this particular solution we have just found. That's it. Well, one last twist. I told you this is a very long thing. I'm splitting this section into two pieces. We'll do the first part today, and then we'll finish the other part next time on variation of parameters. That's the technique that works when this table doesn't work. Well, suppose I have a function on the right-hand side that's not in the table, but it's a sum of two functions in the table. Here's what you can do to solve those problems. I just look for a particular solution that's the sum of yp1 plus yp2, where yp1 is the solution of the problem with just f1 of t on the right, and yp2 is the solution with just f2 on the right, and then the sum of those two solutions to these problems with just one of the functions on the right is a solution to the problem with the sum of the two functions on the right. So what we do, and here's the proof. Let me not go through it again. It's very similar to the previous one. You can look at that. But here's a problem. Suppose I have y double prime plus 3y prime plus 2y equals e to the t plus e to the minus t. That looks kind of familiar, doesn't it? We solved this one before, didn't we? And we solved this one before. What if it's the sum of these two? Well, we remember that the solution with just e to the t on the right was 1/6 e to the t. And the solution with just e to the minus t on the right was t e to the minus t. So what's the solution with the sum of those on the right? Is the sum of these two solutions. 1/6 e to the t plus t e to the minus t is the solution to the problem with the sum of the right-hand sides. There it is. So here's I should call this YP, a particular solution to this problem. There's kind of an interesting note here too. And then the general solution of the problem would be the thing we had before. The homogeneous solution plus this would be the general solution. So this is a particular solution to this problem. And I want to point out kind of an interesting thing has happened here. What really is this right-hand side, if you think of it, sorry, in this problem? Remember something called sinh, hyperbolic sine? It was e to the t plus e to the minus t over 2 is hyperbolic sine of t. I just learned how to solve the problem with something that's not in the table. Hyperbolic sine and hyperbolic cosine you can actually deal with if they're on the right by writing down a sum of these exponential functions. This is actually just 2 sinh t, so I found a particular solution when the right-hand side is 2 sinh t. So there are actually functions you can do that are not on the table. It works if they're hyperbolic sines and cosines, because you can do this kind of thing that we just did, and it works if they're the sum of any two things that are on the table, including these also. It's hyperbolic trig functions. Alright, I think I'll leave this one out. That's enough for today, and I didn't put any of that stuff in the homework. Try some of the homework problems.